Hello, my name is Josh Colson. This is for COT 5405, Fall 2021, and today we're discussing the element distinctness problem. So the problem, given an array with n elements with any arbitrary number, are all elements in the array distinct? And so this is simply just a yes or no answer. Yes being all elements are distinct, and no being there exists at least one pair of elements that are not distinct. And so, given an example, so we can see on the right side over here, top right, 0, 1, 2, and 3. So our array element size of 4. We have 1, 2, 8, and 7. So all these elements are distinct. So we'll say true. But as we see on the left side, on the top left, this array of 7, we can see 1, 2, and 3 are not distinct. So some additional details of this, our model of computation is comparison, and so we have greater than, less than, or equal to. And so just giving some examples, comparing 2 to 3, x to y, or saying 5 equals 5. So the trivial solution for this is sort all the elements and compare adjacent elements. This will give us n minus 1 comparisons, and this will give us a big O notation of n log n runtime. And so the big question now is, can we do this without sorting? Or even better, can we even condense our runtime down faster than n log n? And so what I'm going to be showing is the proof of the lower bound is omega n log n. And so what we're going to be doing with this is we're going to be doing a binary decision tree model with input x containing elements x1 to xn. And so what we need to do for this to compare, to make sure all are distinct, is compare x1 to x2 to x3 to xn. Then we go on and do x2 to x3 to x4 to xn, and so forth. And so what this gives us is n factorial leaves, where each leaf is a yes answer, yes being yes, all elements are distinct. And so as we see here on the right, we do have 3 elements, A, B, and C. And as we see at the bottom, our leaf nodes are 1, 2, 3, 4, 5, and 6. And so I'm going to go ahead and prove this. And so how I'm going to be doing this is I'm going to be plotting our array on ND planes, n being the number of elements. So given an array size of 2, we can see right here, if we say y equals x and x equals y, it's the same thing. But as we go on this line, 1, 1, 2, 2, 3, 3 to n, all those elements are not distinct. But let's say I have an array of 1, 2. I would go on the plane, and it does not fall in that line y equals x. So yes, all elements are distinct in that array set. And another example, 1, 0. All elements in that array are distinct. So let's furthermore move to a third dimension. And in this case, anything that falls on this plane will be not distinct. And so as we see in example A, B, and C, there contains an element that is not distinct. And so they all fall within this, this shaded plane area of some sort. And so going from there, we can then talk about the number of comparisons. So I have to compare 1 to 3, 1 to 1, 3 to 1, 1 to 3, 1 to 1, and so forth. And so what I get from here is 6 comparisons when doing a third dimension. So with this knowledge, we can go ahead and recursively build a generalized statement. So with one dimension, we only have one yes solution. Yes, it is distinct. No, being it is not distinct. 2 dimensions, there exists a way on this decision tree that there are two ways to obtain a yes solution. 3 dimensions, there are 6 solutions for yes, so a permutation where I can reach that gives me a yes answer. So I can start with the last element and work my way back, or start in the middle, and every permutation possible. And so this leads us to n dimensions gives us n factorial solutions. So what I can do with this, knowing that I just proved that there has to be n factorial leaves in my binary decision tree, I can go ahead and say n factorial leaves equals 2 to the h, where h is the height of the tree. And so if I solve for the height of the tree, it is log n factorial, which then simplifies to n log n. Therefore, the height of the tree has to be n log n no matter the array input, therefore giving us the lower bound of our algorithm. So these are my sources. This is the same video as assigned in the assignment. And yeah, this was a really cool project. So thanks.